Bismillahirrahmanirrahim. Variational principle. So, in this lecture, we will learn that what is variational principle and where we can use the variational principle. So, in fact, in variational principle, we have two things. One is called action, and the other Euler-Lagrange equation. So, variational principle is basically connected with these two concepts: Euler-Lagrange equation and applications. What are variational principle? Variational principle determine physical laws by minimizing or extremizing, mean optimizing a quantity called action. So we get physical laws from here in the form of Euler-Lagrange equations. We optimize the action, and from that optimal value of action we obtain Euler-Lagrange equation. We will see some example over here. A functional mapping maps a functional map of function into scalar. This is a functional, it's mapped into a scalar. This is a scalar quantity. This is called action. So the functional is called Lagrangian. This L of x, y and y dash is called Lagrangian. And this, in fact, the Lagrangian density is Lagrangian density. So we define Lagrangian density for some dynamical system and then integrate over the whole region to get the action. For a functional, okay, so this is in fact the S. This is in fact the S in the previous one. So somewhere it is written S and somewhere it is written A, but this is S, and S is for some reason I am keeping it S. For the functional, the governing equations are these are called Euler-Lagrange equations. So we have Lagrangian, a function of x, y and y dash in our one-dimensional Lagrangian case, and we have the corresponding Lagrangian partial by partial y minus d by dx partial Lagrangian partial y dash equal to 0. So this is the Lagrangian and this is the Euler-Lagrange equation. This Euler-Lagrange equations is obtained from the optimal value of the section. Keeping the optimality on this section, we obtain this these Euler-Lagrange equations, and this is one for one dimension, but if we have two-dimensional Lagrangian, then we will have two Euler-Lagrange equation, and it depends on the value number of dependent variables. How many dependent variables are there? So if there are two dependent variables, then we have two Euler-Lagrange equation. If we have three dependent variables, then we have three Euler-Lagrange equation, and so on. These Euler Lagrange equations are derived from the action optimality condition, and we will do to derive this Euler Lagrange these Euler Lagrange equation. In fact, this is not one Euler Lagrange equation. Euler Lagrange equation is for one dimensional Lagrangian, but in physical cases we have many dimensional Lagrangian, and we have that much Euler Lagrange equation. So the Euler Lagrange equation will be derived with detail in some videos and lectures later on. Okay, so let me study first example 1. Shortest distance between 2 points. This is the action, this one is the action which define the shortest distance between 2 points. So let derive it. This section we have a space, we have a curve, and we define the Lagrangian density as, you see over here, we can this total length is S. So we here define ds, and there ds, here is dx and dy. Okay, so using Pythagoras theorem, we have ds square is equal to dx square plus dy square, and taking the root on both sides, so we have ds is equal to under root dx square plus dy square, and it is arc length, so it is positive, so I am taking only the positive root, and it can be written as ds is equal to 1 plus dy dx square under root and dx. So I take dx square common after root, that is only dx, and it is 1, and that is dy by dx square. So now we define this is the Lagrangian density for this one 1ds. There is many ds be defined along the curve and should be added to get this total length of this curve, that is S. So when I integrate, you know that integration from some point, let's say starting point, some starting point x1 to ending point x2. Okay, so that I will integrate on both sides. On the left side I will get S, and on the right side this is integral from x1 to x2 and under root this is under root 1 plus y dash square and dx. So this is exactly what is written over here. So that is the arc length of the curve, and that is why I keep it S. So that is the arc length of this curve from point 1 to 2, and inside this function is called the Lagrangian. Now this is the Lagrangian. Okay, for this case, this is the arc length minimizing Lagrangians. So I'm writing over here L is equal to 1 plus y dash square under root is the arc length minimizing Lagrangian. Okay, this is the arc length minimizing Lagrangian density. We define it for this little ds, and there are many little ds along the curve, and we add them. Adding them mean integrating them. So we integrate this Lagrangian density for the whole curve, and we get the arc length. So this is a simple example for the variational principle, how the variational principle action is defined. So here the physical quantity is arc length, and we define for the arc length we define an integral, and inside the integral is a functional which is called the Lagrangian, and this is very easy and understandable, you see. So we will find the Euler-Lagrange equation. Euler-Lagrange equation give a straight line over here. So what will be the shortest distance between these 2 points? What will be the shortest distance between these two points? That shortest distance will be given by the straight line, and you see we will define the Euler-Lagrange equation for this Lagrangian, and then solve the equation that will give us a straight line. The clear cut shows that the shortest distance between 2 points will lies on the straight line. So what are the Euler-Lagrange equation? The Euler-Lagrange equation is partial by partial y partial L by partial y minus d ds x partial L partial y dash. So this is 0 because in the Lagrangian there is no y, so 0 minus d by dx, and this will give me, you see this is under root, so let's do it here, partial L partial y dash that will give me y dash, okay, under root 1 plus y dash square. When you differentiate this function with respect to y dash, we will get this one. So here this is y dash over 1 plus y dash square under root, and it equal to 0. So when we integrate it, once this plus minus sign is gone because this is 0, so divide by minus sign both sides, so that is gone, and integrating what we will get that y dash is equal to some constant. After integration this 0 will become a constant, this integration constant, and here, so let me write over here, this is 1 plus y dash square under root, so this give me y dash is equal to c under root 1 plus y dash square. This is the Euler-Lagrange. In fact, this is the Euler-Lagrange equation, but I simplified it, and one time I integrated. So I want to see that what the solution of this Euler-Lagrange is taking square on both sides. We have taking square, y dash square is equal to c square minus plus c square y dash square. So this will give me 1 minus c square y dash square is equal to c square. This is c square. So overall y dash is equal to, dividing on 1 minus c square and taking root, that will give me plus minus under root c square 1 minus c square, all are under root. That will be the case after finding y dash from here. Now integrating it, we will get that it is a straight line. Y dash, y, not y dash, y is equal to plus minus under root c square over 1 minus c square x and plus some constant. So you see this is a straight line. So this is a straight line between these 2 points. So what is the shortest distance between the two? The shortest distance between 2 points lies on a straight line, and you see we find the arc length Lagrangian. We use this Lagrangian, the Euler-Lagrange equation. We get a differential equation. We solve that differential equation, and it tells us that the shortest distance should lies on a straight line. This is C1, some other constant, not this C. So the shortest distance between 2 points lies in on a straight line. And what is this? This is the arc length minimizing Lagrangian. So the arc length will be minimum when it is on the straight line. Okay. Second example. Okay, what is this Lagrangian? You see, this is kinetic energy and this is potential energy. This Lagrangian is in fact kinetic energy minus potential energy. So this is kinetic energy, we know it, 1 over 2 mv square and 1 over 2 kx square. So this is the potential energy for spring and mass system. You see we have a support and we have a spring over here which is placed on some, let's say, table, and there is a mass and we pull it on the right and release it, then the mass oscillate in some region. Okay, so in the potential store in the spring is that is 1 over 2 kx square, where k is the spring constant, and due to motion there is energy, that is kinetic energy. So this is the Lagrangian for this system, for the motion of this system. The mass m is attached with a spring and the force is applied to pull it on the right and then release. It will oscillate in this region, and for that oscillation this is the Lagrangian. So this is the Lagrangian density responsible to oscillate the mass m in some region. So this is the Lagrangian density for this phenomena. Spring mass system you studied many times. This is the Lagrangian, and this is the Euler-Lagrange equation. So we have to derive it. The Lagrangian, the Euler-Lagrange equation is partial by partial. X is dependent over here and time is independent. So partial L partial x minus d by dt and partial L partial x dot equal to 0. So this is the Euler-Lagrange equation. Differentiating this equation with respect to x, so that give me to cancel kx. So this is kx. Differentiating with respect to x, only from here we will get kx, okay, but with a negative sign. This is negative. Then I will differentiate the Lagrangian with respect to x dot. From here we get mx dot, and that is 0. So this is minus kx, and differentiate it again. This is mx double dot equal to 0, dividing on minus sign both sides. So this is the case. You see, this is the Euler-Lagrange equation going over here. So the Euler-Lagrange equation for the spring mass system is this. The solution of this, so what is this x? This is displacement from the mean position. Displacement from the mean position. Okay. So find it when it is simple harmonic motion equation, and we know that its solution is this is mx double dot plus k over m x equal to 0. So d square plus k over m equal to 0. So this will give me two Pauli complex root. D is equal to plus minus under root k over m. So solution is x is equal to c1 cos k over m under root t plus c2 sine under root k over m t. So this is the solution. So the displacement is behaving like a wave. Combination of sine and cos. Okay, so we have a Lagrangian. We find the Euler-Lagrange equation, and this Euler-Lagrange equation in fact describe the whole dynamics under this Lagrangian, and we know it is spring mass system. Okay, application of variational principle. So classical mechanics, quantum mechanics, general relativity, optics and engineering, in all you have what is the basic principle. For all of them there are phenomena, dynamical phenomena, for which we will define the Lagrangian and then Euler-Lagrange equations. And the Euler-Lagrange equation, the solution of Euler-Lagrange equation will give us in fact the behavior of the given systems. So for all these and many more, you can define Lagrangian for any dynamical system. Let's say we have a biological dynamical system. So for a biological dynamical system, we can define Lagrangian, and we can discuss the dynamics of the Lagrangian for the given system. So not I take only these 5, but in biological system are also dynamical system. They change with time. So the all those system which are changing in time, for all of them we can use variational principle and we can define Lagrangian. So it's a research area to find Lagrangian for given dynamical system. So there are application in these and other fields. Unified formulation of physics. So everything of the system goes into the Lagrangian, and discussing the Lagrangian, we discuss the behavior of the given system. Symmetry analysis. There are symmetry connected with the Lagrangian called another symmetries, and we will discuss in some videos Lagrangian and their another symmetries. So there are symmetry analysis which help in understanding the dynamics of the given system. Conservation laws, why another symmetry? So once we get the another symmetries of the Lagrangian, then there are conservation laws connected with the another symmetries. So Lagrangian formalism gave us everything in unified formulation. We can understand things using symmetries, nodal symmetries, the conservation laws in the system easily by this technique. Variational principle provide a powerful and elegant framework for deriving physical laws, and the physical laws are deeply connected with the Euler-Lagrange equation. Euler-Lagrange equations are in fact second order differential equations. If we are in first order Lagrangian, so our Euler-Lagrange equation are second order differential equations, and we solve the Euler-Lagrange equation and get the behavior of the system. Also we use this principle to find the nodal symmetries of the Lagrangians and the corresponding conservation laws. So variational principle is an easy way to understand dynamical system. Okay, thank you. If this is helpful, then like, comments, and subscribe. For improvement. Thank you.